So now I want to give a talk a little bit about Go programming, and I'm mainly going to walk through a few slides here. I'm not going to do any live coding in this talk here. So these slides are really based on some slides from several people at Google, and let's get going. So first of all, Go is a modern programming language. Takes inspiration from a lot of other programming languages. It's sort of object-oriented, but it's not fully object-oriented in the usual sense that you might learn in Python and Java and such. But it has most of the features that object-oriented programming offers. It provides strong support for concurrency, and that is something that I'll talk about specifically in a separate talk later on. It's a really nicely designed language in the sense that it's concise and compact. It's designed to be readable in a sense. It's what we call an imperative language, just like Java and many other languages. It's not like Haskell, which is a functional programming language that some of you might have heard of. It is also statically typed, and it has dynamically type-safe features. It's garbage collected, and it compiles to native code statically linked in the usual case. So that means that you can compile and get one binary. You don't need a Java virtual machine or a Python interpreter to run your program. It's also got quite fast compilation and efficient execution of the program. So it's a relatively efficient language. It's not comparable to really low-level languages like C, but at least on par with Java and more efficient in many cases. So that's sort of a brief summary of the features. A little bit of the history. The design really began with three people, Robert Griesemer, Rob Pike, and Ken Thompson, which are two of them. Rob Pike and Ken Thompson are from Bell Labs originally. Ken Thompson is one of the designers of Unix, and Rob Pike is also one of the people that was heavily involved in the Unix development back in the good days at Bell Labs. Anyway, these three guys were later joined by Ian Lance Taylor and Russ Cox, and Russ Cox is currently the leader of the team developing Go at Google. It's been open sourced in 2009, and the first release was in 2012 early, and the most recent release is Go 1.15, was released just a week ago or so. And this most recent release is still what they say compatible with Go 1, meaning that if you wrote the program with Go 1, it is most likely going to compile, or it's going to compile with today's compilers. All right, so this talk was originally designed to compare Go and Java, and I do have some bits that compares Go and Java, even though some of you might not have programmed in Java. I've removed most of the parts that compares things with Java, but there are some things that sort of make sense to compare with Java if just to talk around them. So both languages have many things in common. They are C family. They come from the family that separates or writes functions or methods using curly braces. to demarcate the beginning and end of a function, which is sort of different from Python, which has indentation-based scoping. It's statically typed. What does that mean? It means that we're required to, in most cases, to specify what type a variable should be. And I'll show some of these statically typed variables in a minute. The program Go and Java are both garbage collected languages, and that means that we don't have to manage memory manually. So whenever we need a variable, we don't have to do malloc or do something special to sort of free up the memory after. In C, you have learned, if you've done LAD2, that there's something called malloc and free, and that's what you don't have to do in Go. It's what we call memory safe, in the sense that it has bounds checks when you're accessing an array and these type of things. It's got nil references, so you can say that something has not been initialized yet, for instance. It's got variables, and they're always initialized to their 0 value, which is sometimes a nil value. For instance, if you have a reference or a pointer to something, then it's the 0 value is nil. It has support for methods, interfaces, and type assertions, and reflection. We won't talk much about reflection in this course, but it's a feature that modern programming languages have, and allows you to do sort of runtime decide what code to execute and stuff. Anyway, the ways that Go differs from Java are listed here. So first of all, it compiles the programs to machine code, so there's no need to have a virtual machine or a Python interpreter installed on your machine. If you compile a binary compile a binary for your architecture, for instance, a Linux machine or a Windows machine, then it's going to run on that machine without having to install some extra software to be able to run the code or the program. So in that sense, it's similar to C. It's mainly got statically linked binaries. So what that means is that if you import some library or import some functions from some other source, then it's not it's what we call statically linked. It builds everything into one binary, and that has some nice advantages in that you can send or copy that one binary, and it will just run always. The drawback, of course, is that a statically linked binary tends to become big because it has to include all of the dependencies that you depend on. So that's a pros and cons things. But recent versions of Go has support for linked libraries as well. I have not used that myself, so I can't really talk too much about it. It has relatively good control over the memory layout, so you can sort of control how your structs or data structures are organized in the memory, and that has some performance benefits that can be important sometimes. It has something called function values and closures, and that's a language construct that has become popular in coming from functional languages like Haskell F sharp and other such languages. Actually, I think Java has the same type of features nowadays. So this slide is really a bit old, and I forgot to update this part. But it's got built-in strings, UTF-8, so you can write Norwegian characters or Chinese characters or whatever you like in the language itself. Although we don't recommend using Norwegian characters or Chinese characters for that matter in variables, because that can sometimes cause problems. It has built-in generic maps for an array's slices. That's something that sort of Java has generics, but they're not built in the same sense. So that, just to point out that Go itself doesn't really have generics in the way that Java and C# does, but that is coming in a few years' time, 1 or 2 years probably. They have a design that is more or less ready, so probably next year, or we can already try it actually. They have an implementation of the generics implementation, so you can play around with it. There is built-in concurrency, and that is sort of one of the prime features of Go. We'll talk about that in a future lecture. All right, so Go has a goal of being readable, and for this reason, this and other reasons, the designers intentionally left out many features that some other languages have put in. For instance, there's no classes, there's no constructors, there's no inheritance, and there's no exceptions, and so on. So there are many features that have not been included to keep the language simple, and this, most of the time, it just becomes easier to use when you don't have to know about the notion of constructors. You can just use functions to do construction. So many of the things that people sort of miss when they come to the language at the first time is really just a different way of doing the work. All right, so the point with leaving those features out is to make code readable, as I mentioned. And we read code like 90% of the time, and we write code 10% of the time. It's like a rule of thumb statistic. And so we should really strive to make languages that are easy to read and comprehend. And if something is a little bit more difficult to write, then that is probably a compromise we want to make. And so I just checked for probably a few years ago, and back then Go has had 25 keywords, whereas Java has about twice as many. I didn't update this, and I don't think Go has not added any keywords. I don't know what Java has done recently. C# has more than 100 keywords, so C# in that sense is a relatively complex language with lots of keywords. I linked to 2 very interesting blog posts here, especially the last one, Go at Google Language Design in Software, in the Service of Software Engineering, and that's a really good blog post describing many of the design decisions that went into designing Go. All right, so let's get going with some examples here. So at the top here, we see how you would write the Hello World program in Java. Obviously, Python is very simple, so you can find similar talks to this that compares Python to Go as well, if you want to do that. This is how you would write Go, hello world in Go. So all programs have Go programs have this structure that it has a name, a file name, and .go. There's some files that have underscore test or something like that are test files. Every file starts with a package declaration. So in this case, package main. So this is typically the package where the main program or the main function resides. So basically, if you have a package main, one of the files in that package must have a func main in order to be able to run your program. In this case, we are importing a package called FMT, and FMT is short for formatting. And so FMT formatting has this print line function that takes a string and prints it to the standard out console. So this run button here should ideally allow me to run these programs in this slide deck, but for some reason there is a bug in this tool that prevents me from running these programs. At least they seem to only work after pressing many times, and that's just gonna be a bit bothersome. So I'm not gonna continue to try running those programs, but you can copy paste the programs from the slides and try them out in your own editor if you like. Here's another program. Here is it's basically a web browser. No, I mean a web server. So if I were to run this, it would start a web server on localhost on the machine. You could then put this address or the URL here into a browser in order to hit this server. And the way that this works is that it calls whenever you hit this endpoint, we call this. Whenever you hit this endpoint, it's going to call this handle hello function that is defined down here. So here you have a handle func that defines an endpoint and provides a function that should be called whenever this endpoint is accessed. And this hello func then takes HTTP request that you'll probably learn more about in web programming course. It takes this request, it looks up the URL in the request and prints out that it's serving this particular URL, and then it prints so it prints this on the server side. Basically, it would show it in this window here, and it sends back to the client, the web browser, this string here, hello world. And this is basically writing this. So it's using a different function called fprintf or fprintline, and it's writing that to this response writer. So that's basically where you send back the result to a client. Okay, so there's a few things to note beyond just the basic function of this program, and that is that the types here are sort of or the names of the type follow the declaration. So so here you see, for instance, W is followed by the type, and here request, which is sort of the argument to the function, the W and request is the argument to the function, is followed by the type of that of that variable. And so this is different from Java, and I'm not sure if you even think about types in Python in that sense, so you probably don't have this thing here. But the nice thing about keeping these types is that you are defining a function here, handle hello, and you're telling the reader of the code that I'm expecting this type and I'm expecting this type as input. And that means that as a user of this program, you don't have to wonder what is the type that this function expects. So that's one thing. So it's more readable. And also, these can be compile time checked. So when you compile your program, the software or the compiler will tell you whether or not you have provided the correct type as inputs here to this handle func. This handle hello function. Another thing to note here is that in languages like Java, I'm unaware of how it's done in Python, but in Java, you have these public and private and protected declarations in front of variable names, and this is different in Go, where we say that functions and variables that are capitalized, like the fatal function, the printline function, and the HTTP handle func, these are exported, meaning that if a function has a capital letter in the beginning of the function name for this or in this package HTTP, then that is an exported function and you can access it from another package. So I'm now in my main package here and I'm using HTTP handle func. So we say that HTTP package is exporting the handle func function because it's got a capital H here. And similarly, the FMT package exports the printline function because it has a capital P. And if you have a smaller case or lowercase printline function inside the package FMT, you couldn't or you can't call that function, so it's not exported. All right, so let's move on to a little bit about types. And so in Go, we have, as in Java, what we call primitive types. And they are typically ints of various sizes. So there's int, uint, which is unsigned integers, and there's int8, uint8, uint or int 32, and so on up to 64. And there's Boolean, there's string, and these are called primitive types. There's floats, two types of floating point, so these are decimal numbers, and there's also complex numbers if you need to compute Fourier transforms or whatever. Then there's structs, and they are declared in this way in Go. You say type and the name of the type and struct followed by curly braces, and then you say the composed part of your struct here. So person is like a combination of different types or different variables inside this person. So this would be sort of like a class in Java or in Python, but it's really just a struct. We don't, at this point, we have not added any methods to the person type. So the person type here has two attributes. It has name and age, and the name is of type string, and the age is of type integer. All right. So in addition to these primitive types and the structs, we can also have pointers, and pointers are written with a star in front of them, like this. And we'll get back to a little bit more about pointers in a minute. We have functions, obviously, and they're written with func as the keyword, and then you may have arguments to the function, and you have the return type of the function on the right hand side here. We'll see more about functions also in a minute. We have a notion of channels, which is something that's sort of unique to Go. It's a construct that allows you to coordinate activities between what we call Go routines, and that's related to concurrency or parallel execution, and we'll talk more about channels in that lecture about concurrency. Also, we have interfaces, of course, and that's relatively similar to Java interfaces, but there is a difference, and I'll get back to that also in a minute. All right. So there are sort of two main built-in types, or data structure. Data structures, and the main one is slice, or the two are slice and map. Slices are like a list. It can, but it's not a linked list that you'll learn about in data structures, but it's like an array where you basically keep the elements next to each other in memory. And this slice can then grow and shrink, and it has a length and capacity. So the length basically means that it has a length defining how many elements it has, and it has a capacity telling how many elements it can hold without having to resize or grow the capacity of the slice. So you can think of it as a dynamically sized array, and it's possible to do many operations using slices. For instance, if you want to access the ith element of the slice, this is how you would write it: s and these brackets, angle brackets, and the index I into. So you're basically indexing into the slice s. Here you can do compute how long it is, basically what's the length of how many elements it has currently. You can index using this colon notation, and that gives you back a slice that maps to the same memory region as the original slice, but it excludes everything before I and everything after j of the original slice s. So if you declare or assign that to another variable, say m, then that would allow you to access only part of the original slice s. And there's a special function, append, that takes the slice as the first argument and another element that you want to add to the slice. So x is being added to the slice, appended to the slice s, and you actually have to append or assign that back to either s or to another slice in order for that to have an effect. All right. There's also maps. In Python, I believe they are called dictionaries. So a map is defined in this way. You specify basically map, and you give it a key type. So you specify in angle brackets here a key type, and after the bracket you specify the value type. So that basically gives you a map from some type key or k to some type v or value. So it's basically a language supplied hash table or dictionary, and basically map of values of type k to these type v types. So these are just user replaceable, and here you see an example of how you would use a map. So you would make so this is like a function, and the make function can take either a slice or a map to make it, and you would specify something like this in order to create a map from a string key to some integer. And here we declare var m, so we're saying that m is of type map from string to int. And we can use this map m in this way here. So we pass it the key, this string here, and an integer on the other side of the equal sign here. That's how we assign the 2020 to the key .320 inside the map. So we can do a lookup just by using this. If we have m and pass it this key, we should get back this if we write a function or just use this in our code. All right, let's move on. And you can iterate over a map. So if m is our map, we can iterate over it with a for key and value, and colon equals means that we're declaring these two variables, key and value, but we're ranging over m. So for every time we loop through the for loop here, we're assigning key and value from all of the entries in the map. One important thing to note here is that every time you do this iteration over a map, the order may be different, and probably is different. So if you iterate over a map and you get the same result twice, that's just pure luck, or so it's not something that you should rely on. If you need to have an ordered output from a map, you have to sort the keys and then do a lookup as you iterate over it. All right. All right, so moving on to these type declarations. So if we want to have a struct, for instance, there is the keyword type that expects to have some name, be followed by some name, and a specification. And the specification for a struct is like this, and you can have similar specifications for interfaces and other types. For instance, you can have a type Celsius that is of float 64. So you can basically define a type for Celsius that is the same as a float 64, but you can reason about degrees in Celsius separately, or you can analyze statically at compile time that you're passing into a function a type that is Celsius and not some arbitrary float. Yeah, we already looked at the person struct previously, so I won't go through that again. There is also function declarations, and they're defined in this way. If you have a func, or functions are always start with this keyword func, followed by a name of the function, followed by parameters of the function in parentheses. So it can be one or more parameters, or zero or more parameters, and it can return zero or more return values. So here's an example of a sum function that takes two integers as input and returns an integer. And here we see that the variable or the input argument a is preceded by the type int, and similar for the type for the variable b, it's preceded by the int keyword or the type. And then it's possible to, if the two types are the same, so if a and b are both ints, we can write it in this shorthand form as well. We can also have multiple return values. So we can return, for instance, in this division function here, we can return both the division value, how much is a divided by b, and we can also return the quotient or the reminder of dividing a and b. So this percentage is basically the modulus or the reminder of this division operation. And we can also, obviously give them more intuitive or clear names, denominator and the dividend here. So that's so we're not using these in the function itself, but you can also declare return value names here. So q then becomes associated with these with this division, and the modulus or the reminder gets associated with the rem variable. So you can use these also inside your function declaration here. Okay. Now, methods is really just functions in disguise in Go, and this is how we declare a method. So a method is something that operates on a struct in Go, and so we declare it in the same way, but instead of just giving a name of the function and parameters and so on, we actually specify in parentheses a receiver object or struct. So here's an example, func, and we have a receiver of type person, and in order to access a specific person object, we use this shorthand p. So this would be sort of corresponding to self in Python or this in Java. So instead of always using this or self, we can now specify ourselves that we want p to be our refer to the object at hand. And so this is sort of the method name, and it's returning a bool. And in this case, it's just checking the age of the person by p dot accessing the age of the person object or the person struct. Now these functions here in Java, at least, I'm not sure in Python, but in Java you specify methods inside the person class. So you sort of put a bracket around all of the methods that belong to the person class. But in Go, you instead specify just a bunch of funcs with these receiver methods, or methods are basically these functions that have these parentheses before the function name. All right, so we can also add methods to primitive types like float64 by doing it via a custom defined sort of like this custom defined float64 Celsius here. So we can create a function free or a method freezing that checks whether or not a given Celsius value C is less than or equal to 0. All right. So there's one limitation to methods, and that is that they can only be defined on types declared in the same package. So you cannot say that I want to have a method length that operates on types in another package or from the standard library or the primitive types like here. This is not allowed. So you have to be in control yourself of the package where the type is declared. So if you control the person packet or the person type, then you can declare a function like this in the same package as the person type is declared. All right. All right, so pointers. Pointers are a nice abstraction that allows to access the address of a variable. And that's useful in many cases. For instance, if you have a large data structure containing many elements or things like that, then you can pass an address to that data structure to a function, and that function can operate on the original data structure rather than having to copy the data structure into a function. And pointers in Go use the same notation as pointers in C. And so if you declare a variable here, a string hello, and assign it to the variable A, by the way, this colon equals is the assignment operator. And you can write assignments like this in Go. You can also, if a variable is already declared, so if A is already declared, then you don't use the colon equals. So if you use colon equals, you're actually both declaring the variable as a string at the same time as you're allocating or initializing it to the value here. All right, so in order to make a pointer or take the address of this string hello, we use the ampersand and the variable name in order to get a pointer to this string in the memory. And that is then assigned to this variable p here. And in order to use this this address of A here, or this pointer, we have to use the star thing here to in front of it to dereference the pointer. So we're getting a pointer p, and in order to use it as a string again, then we have to put this star in front of it, meaning that we're dereferencing the pointer, or looking not at the variable itself, but looking at the content of the memory that it's pointing to. Now, different from C is that Go doesn't allow what's called pointer arithmetic, basically meaning that we cannot do +4, or take the address of P, or basically the address of A, and look at the 4 bytes beyond. So if this is the 0 byte, the fourth byte would be something like here. We can't sort of make P point to the O instead, like this. We can only point to the beginning of the string here. And that is a good thing, because doing so, these pointer arithmetics is not a safe operation, because there's nothing that would stop us from adding 6, which would go beyond the limits of the string here. So that's not legal in PureGo. There is an unsafe package that allows you to do more unsafe things, but we won't look into that here. All right. Next is looking at how we use these pointers. So we can pass things by value. So here we're passing a variable x by value, and this has no side effects, meaning that this is just a function. Whatever we pass in here is going to have no effect on some person object or some other object. So what this is doing is taking the x and doubling the value of x, and it's not even returning it. So we're not making any changes. However, if we pass this x as a pointer, then it's possible to see the effect of this double function here. So here we're passing the variable x, but that is a pointer to an int. And we're taking this here as a pointer, but in order to use the pointer, then we have to use the dereference operator here. And we're still doing the doubling, or the multiply by 2. And we're now actually changing the actual value of the passed in variable x. So if we pass in some variable x, we're actually changing the resulting, or the original x that was passed in. And so it has side effects. It's visible outside the double function here. And that is not the case for this first double function. Here it would basically just do the doubling, and then it wouldn't be visible outside this function that it was doubled. So it's a useless operation here. Yeah, so passing by value is often done still, but it's if you need to have some result from a function like this, you better return it, or make some other use of the variable here. All right. So these these method declarations can also access or use pointers. So here, the receiver, which is on a receiver on the person type, is actually a pointer to the person type. So what we're aiming to do here is to increment the age of the person, and so we're basically calling the ++ operator to increment by 1 on the person's age field. And in order for this to work, this type better be a pointer, because if we don't use a pointer here, this would effectively have no, so if there was no star here, this would be like a pass by value, and we would just do an increment of that value so it would copy the person object, and it wouldn't really change that copy, or it would change the copy, but it wouldn't change the original person object. So the receiver method, or the method receiver, is a copy of a pointer pointing to the same address. So these function types like this, they are really equivalent to doing something like this. So this function does not, or this method does not have any input arguments, but it's the same as moving the receiver here as the first argument to this ink age thing. And as you can see here, we are passing in a pointer to the person, allowing us to update the age. Again, if we didn't pass in the pointer or a pointer to a person, we would just send in a copy of the person's object, and we would update the age on the copy. But since we're not returning that copy or updating the original one, that update of the age is not going to have any visible effects outside of the function. Yeah, so these two functions, they operate on the, again, on the pointer to a person object. And so these two functions have identical behavior. Yeah, and here is exactly what I explained. If we do not pass or use a pointer here, this is not going to update the age of the person object or the original person object, because this becomes a copy of the original person object. And this is a minor point, but this person pointer can actually be a nil value. So we can actually use that if we didn't initialize the person, or we're using the 0 value, which is nil, then the person name would not be initialized. And so in this case, we can check if the person type has not been initialized using this check, and return anonymous in this case. Okay, so coming to interfaces. So in Java, interfaces are declared like this. In Go, sort of different interfaces here, but they're defined in this way, with the interface keyword after the name of the interface. And we basically have a bunch of, or one or more methods here. We can also have empty interfaces, which is useful. But yeah, so one thing that is important to note here is that in Go, it's common to name interfaces with a word closer. So we would have a opener or a closer, or there's a writer and reader. So these are interfaces in Go, and it's common sort of to name them as with a ER ending. So the key difference between interfaces in Go and other languages is that they are implicitly satisfied. And what does that mean? Which is different from Java, where you explicitly have to say that this class is implementing an interface. In Go, we have this implicit satisfaction, and that means that if a type defines all the methods of an interface, then the type satisfies the interface, and we can use that type as if it implements that interface. And this gives some benefits for software engineering, like fewer dependencies, and we avoid some kind of type hierarchy. That's some of the problems with Java, and it allows easier composition of types. All right, so let's take a look at some examples here. So interface types can be empty. So this is a legal interface. doesn't have any methods. So you can sometimes see function signatures that expect a interface or an empty interface as an input argument, meaning that it can accept any type as input, because any type does not need to implement any methods. So it's a legal concept. Here is a stringer interface, and that's like in Java. There's also a standard function called toString. In Go, this would be sort of the equivalent. So the stringer interface would just be one method string that returns the native or the primitive type string. So this is a method that returns one of the primitive types string. Here is a bit more expanded interface called just interface. This is a part of the standard language or the standard library. And these, if you implement this interface, then you're implementing what's necessary in order to sort the values that of the type that you're implementing this interface on. Okay, so let's take a look at using the stringer interface first. So we have we can declare a point type that takes x and y coordinates. I seem to have forgotten one of the slides, but you can declare the type a struct, just like the person, that takes an x and a y coordinate or something. And you can declare a variable x in this case that is a point. X is a stringer type, and you can assign a point to the variable x, and you can then use this type x or this variable x as a stringer, because it implements the stringer interface. So you can call the string method as long as there is a implementation associated with the point type here. And here we're actually reassigning the same to the same variable x. It's still a stringer type, but we're assigning it a weekday, which is another type that I didn't show, that also implements the stringer interface and allows us to again call the string method on the x variable here. Now, what's interesting is that the FMT println function knows about the stringer interface. So if you pass in to the println function any object that implements the stringer interface, like point and the weekday type, then println will know what to do. Basically, these would be equivalent to calling the string method on the type here. Okay. So I mentioned this interface, which defines length, swap, and less. And as I mentioned, this is what's needed in order to sort some data or sort some type of data. So if your type here, lexical, contains a slice of strings, so this is how you declare a slice of strings. So if the type lexical is a slice of strings, then you can define these functions like this. We're making them, or methods rather. So the length function method operates on the type lexical, and in this case it just returns the length of this type or this lexical object, which is a slice of strings. So this is basically looking at how many elements are there of this slice or this list. And then the swap operation is basically doing swapping the two positions I and j in the slice, and the final one here is the compare operation, basically comparing the elements at position I with the position j and return true or false depending on whether or not AI is less than AJ here. And if you do this, if you implement these functions on your type, then you can easily then you can just use this sort function from the standard library in this way. So S here is a slice, and we pass it or we sort of cast it or make it into this lexical type that we already declared the sort functions for. So that's how you can implement the sorting mechanism. There are some newer features in the standard library now that allows you to do these type of things a little bit easier for some standard types. So it wouldn't be so, you could do it more easily to a string slice like this now with another function. Okay, so that's sort of the main things I wanted to talk about regarding the language itself. I'm heading over to talk about tools, but just wanted to mention that there are a few other things that we'll talk about later, like the concurrency aspects that I won't touch on today. So one of the things that Go also is good at is that it has good tools. There's this Go funct and Go imports, and there's this Go tool, and there's GoDoc, and it has great support for editors nowadays. So Go funct and Go imports are nice because whenever you run them on your code, it's going to format your code so that it looks nice, basically. So this is, I mean, the compiler will be able to understand your code even if you don't follow it, but it helps readability if everyone uses sort of the standard formatting. So that's highly recommended, and most people actually use this setup in their environments or their IDEs. There is also this Go imports, and so whenever you use a library in your code and you save, it's going to put in the import statements pointing to those libraries that you want to use. So that's also one of the handy tools. But again, this is really the default setup in many of the Go developer tools. The Go tool is also very nice. It's very powerful. Here I just show one command that you can use the Go tool to do. So Go is like you use this to go build or go install or go build is the main one that you typically would use if you are going to compile something. But this go get thing actually goes to this URL here. So it will actually download this command and install it for you. And so after you run this command here, you can just run it with this percent command here. And this is percent tool here is what I'm using to view the slides here. All right, here are some documentation for sort of open source Go. It's not the standard library, but so this was the original one that or the first one that people used, developed as open source, and then the Go team has recently started to create this new one that has some better features and is sort of cleaned up a little bit. But both of them are still running, so you can go to both of them and search for various packages that you need. If you need some YAML parser or a JSON parser or something, you can go look here for alternatives. All right, IDEs. So there's a bunch of them. Goland is one from JetBrains. That's a pay thing. Maybe as students, you might get a free license. Visual Studio Code is the one that I'm currently using. And it's open source and free to use, so it's nice. And obviously VS Code or Visual Studio Code is plugin based, so you have to install the Go plugin along with this. Vim is a popular choice among many Golang developers. It has a nice plugins architecture as well. I've not used it as my main editor, but many people use it. And there's a whole bunch of others that you can choose from. All right. So I guess I should probably mention that my opinion is that Golang has the better refactoring support so far. So I think Visual Studio Code and language server that is being developed, which is going to be cross-editor, is going to improve this refactoring support in the coming years. But so far, Golang seems to be the better one if you need to do a lot of refactoring. Although I don't use it on a daily basis. All right, so that's just a quick summary of some links to more material. I'll point to them in a separate, or they're sort of linked to from the Lab 3 as well. Okay, so that's it. See you in the next one.